Today, my friend Jay Agarwal will be introducing you to optics. He will be explaining the basic theory in optics first.
Optics basically divided into two categories: geometric optics and wave optics. First, we will be dealing with the topic called reflection. Reflection is basically the turning back of light after striking a surface. The surface at which the light strikes are called mirrors. Mirrors are basically of two types: the plane mirrors, which are like this, and the curved mirrors. Curved mirrors are also divided into two categories: the concave mirrors, this one, and the concave mirror, this one. Now we will move into the topic laws of reflection. Laws of reflection basically states two important points: that the incident ray, the reflected ray, and the normal to the mirror all lie in the same plane, and the angle of incidence is equal to the angle of reflection. See, there is one very important point to remember, that in a plane mirror, the image distance and the object distance are same. That is, the distance of the image from the mirror and the distance of object from the mirror is same. Now, maybe we will move to the different image positions for different object positions in a concave mirror. So, basically here C denotes the center of curvature and F denotes the focus. So, when the object is kept at infinity, the image is formed at focus. When the object is kept beyond the center of curvature, it is found between focus and center of curvature. When the object is kept at center of curvature, the image is found at the center of curvature. When the object is placed between the center of curvature and focus, image is found beyond center of curvature. When the object is kept at focus, the image is found at infinity. Now we will move to one of the very important topic of optics, that is Cartesian sign convention. Most of the students get confused in this about choosing sign, so you have to master it properly. And this this sign convention will be involved in most of the questions. So basically, this sign convention is based on the direction of incidence of light. So the direction of incidence of light is taken as positive. So this is the coordinate system which we will use. This is the positive x-axis. This is the positive x-axis. This is the negative x. And this is the positive y-axis. So this direction is considered as positive, and this direction is considered as positive, whereas this direction is considered as negative, and this direction is considered as negative. So suppose we will be moving from this point to this point, the distance will be positive. But if we are moving from this point to this point, the distance will be negative. Now we will move to the mirror formulas, which are also a very important topic in optics. So this should be learned by heart. So the mirror formula says that the 1 by the distance of the 1 by v plus 1 by u is equals to 1 by f, where v, u and f follows the Cartesian sign convention. So remember, this formula should be used according to the Cartesian sign convention. We have to also learn the formula for the lateral magnification in a mirror. The lateral magnification m is given by the height of the image by the height of the object, which is equals to minus v by u, where v is the image distance and u is the object distance. The power of a mirror is given by p equals to minus 1 by the focal length. Now we will move to the other phenomena of light, which is called refraction. Refraction is basically the bending of light. The refractive index mu is equals to the c by v, where c is the speed of light and v is the speed of light in other medium. And mu to 1, that is mu of medium 1 related to medium 2, is refractive index of 2 by refractive index of 1. Now we will be dealing with laws of refraction, which also deals with the two important points. First is the incident ray, the refracted ray and the normal lie on the same plane, which is similar to what we dealt in the laws of reflection. And the Snell's law. which says that the sine of the angle of incidence by sine of the angle of refraction is equals to the refractive index of medium 2 by the refractive index of medium 1, which remains constant for a given pair of media. So the angle of incidence is this and the angle of refraction is this, and mu and the corresponding mu1 is this and the corresponding mu2 is this. Now we will dealing with one of the most important phenomena of light, which is called total internal reflection. So when a light travels from a denser medium and strikes at the interference at an angle of incidence greater than the critical angle, total internal reflection occurs. So basically, when this light in a denser medium travels like this and the angle of incidence when it is greater than the critical angle, the total internal reflection occurs, and hence there is no part of light which gets refracted. In this mu2 is greater than mu1. Remember this is one of the important thing in total internal reflection. Now total internal reflection has many applications like the optical fibers and the sparkling of diamonds. Now we will be dealing with refraction of light at the spherical surfaces. The refraction of light at the spherical surfaces is given by one of the basic formulas, which is this, where mu2 and mu1 are the refractive indexes, and v is the image distance, and u is the object distance, and r is the radius of curvature of the spherical surface. Now, the lateral magnification in the above case is given by the height of the image by the height of the object, which is equals to mu1 into v by mu2 into u. Now we will be dealing with the image formation by convex lenses. So a convex lens which look like this have a positive focal length f1 and a positive focal length f2, and the incident ray is taken to be in this direction. Now you can look at the table and it's similar like in the mirror. Like at infinity, the image will form at the focus f2. Now remember this last one. This is very important, that the object between the focal length f2 and the optical center O will form an image at the same side of length, that is in this side, and the image will be virtual like this. Now the Cartesian system for lens, it is similar to that we dealt in the previous one of the previous slides. Now we will move to the Lenz-Mega formula, which is one of the most important formula in optics and also very important for the JEE point of perspective. So the Lenz-Mega formula states that 1 by the focal length of the lens is equals to the mu2, which is the refractive index of the lens, by mu1, which is the refractive index of the medium in which the lens is in which the lens is there, minus 1 by 1 minus the radius of curvature of one of the side, and the radius of curvature of minus 1 by r2, which is the radius of curvature of the other side. Now we move to the Lenz formula, which states that 1 by v minus 1 by u is equals to 1 by f. Now remember, in every formula that we have dealt with, the Cartesian sign system holds, and we have to choose proper sign for denoting different values. Now we will be dealing with the compound microscope. The compound microscope has two lenses, the objective lens and the eyepiece. The object is kept at the focal length f1, and the parallel rays are produced by the objective lens, which strike at the eyepiece and forms an intermediate image at f1 dash, which is the focus of the eyepiece. After this, the final image rays becomes parallel. The lateral magnification in the above case is given by the magnification of the objective lens and magnification of the eyepiece. This is similar to what we dealt with the combination of lenses. This will get simplified to minus h, which is this distance, by the focal length of objective into d by focal length of eyepiece, where d is 25 centimeter, which is equal to the near point. Now we will move to another optical instrument known as astronomical telescope. In astronomical telescope, there are two lenses similar to as compound microscope. In this, we used objective lens and eyepiece. The main difference is that from the compound microscope is that both the focus of the objective and eyepiece coincide within the telescope, and the object, which is basically a celestial body, is approximated at infinity. The intermediate image is formed at f2 and f1 dash, and the length of the telescope is given by f of focal length of objective plus the focal length of eyepiece. In this case, the angular magnification is given by negative of focal length of objective by focal length of eyepiece.
So now we have reached the end of geometric optics, in which we discussed reflection. In reflection, we discussed the types of mirrors and the laws of reflection and the choice of Cartesian sign convention, which is an important thing to remember. Also, mirror formula was discussed. Then we moved on to refraction, where we discussed the laws of refraction and then dealt with prisms and lenses, the phenomena of refraction and the formulae to be applied for both. In lenses, we discussed lens maker formula. Then we moved on to the various optical instruments like microscope, simple microscope, compound microscope, and astronomical telescope. Now, Jai will walk us through wave optics, the second topic under optics. He will explain the important formulae and important concepts.
Now, in wave optics, we will first start with the Huygens principle. Well, each point source, the Huygens principle basically said that each point source is a center of disturbance from which light spreads in all directions, and the secondary wave fronts arises from the primary wave fronts. So these wave fronts are basically the wave form of light which travel in all directions, like this. Now, the laws of reflection and refraction can be verified by the Huygens principle. Now we are moving to the another phenomena of light due to the wave nature of light, which is called interference. Basically, interference is the superposition of light. Now, there is one important term which is called coherent sources. What are these coherent sources? Coherent sources are the sources which are having fixed phase difference between them, and hence they are said to be coherent, that is independent of time. Now we'll move on to the one of the most important experimental setup for the JEE point of view, that is Young's double slit experiment. In abbreviation, we say YDSE. Now, in YDSE, basically we use two slits S1 and S2, and there is a point source S0 from which light waves emerge, and the size of the holes of S1 and S2 are comparable to the wavelength of light. Now, the light from these two slits will interfere at a specific point on the screen. At this point, the path difference is given by d sine theta, which can be approximated as d tan theta, which is equals to small dy by capital D, where small d is the distance between the slit and capital D is the distance of the screen from the slits, and y is the position of the point. Now, for the constructive interference, we know that the path difference should be an integral multiple of lambda. So from this we get, for the constructive interference, the points are n lambda d by d, where n can be anything from 0, plus minus 1, plus minus 2, or anything, where capital D denotes the distance from the screen and small d denotes the distance from the slits, and n is equal to 0, which is this point which I have denoted as O, is called the central maxima, and n equals to plus 1 is called the first maxima, and the series goes on. For destructive interference in YDSE, the path difference should be equal to the odd multiple of lambda by 2. From this we get the position of point P equals to the odd multiple of lambda into capital D by 2 into small d. Now from the above derivations we can get the fringe width, which is fringe width beta, which is equal to lambda into distance of the screen from the slits by the distance of the slits, where lambda is the wavelength of the light used. Now, intensity at any point P is given by this formula, where cos phi is the angular distance of that point from the center of the slit. Now, if now YDSE in YDSE the experimental setup can be changed by introducing a slab of thickness T in front of of a slit or both the slits. Now, if we introduce a slab of thickness T in front of a slit, basically the optical path increases by T into mu minus 1, where mu is the refractive index of the slab with respect to the medium in which the YDSA is taking place. So, since the optical path increases, the path difference also changes. Now, path difference now becomes S2P minus S1P plus the new added optical path increase, which gives the final optical difference. From this, we will calculate where the constructive interference occurs and where the destructive interference occurs, and hence what is the shift of the YDS fringe pattern. Now, we'll move to another phenomenon of light due to the wave nature, which is called diffraction. Now, diffraction is basically the bending of light from an edge of an object whose size of hole is comparable to the wavelength of light. So, in this A is comparable to lambda, which is equals to the wavelength of light. Now, minima can occur when A sine theta equals to an integral multiple of wavelength of lambda, which will give the position of any point on the screen where the minima occurs as in any integral multiple of capital D, which is the distance of the screen, into wavelength by the distance by the diameter of the hole. So here we get the intensity distribution of the diffraction, which has a very big maxima between, and the amplitude of the maxima decreases as the distance increases from the center. Now we will be moving to the resolving power of the optical instruments. Now, why do we need to resolve power of the optical instruments? So, in the last slide, we discussed about the diffraction of light. So, due to diffraction, the light beam from the lens is not focused at a point, but it is focused into a spot of a finite area. So, basically, it's not a point like this, but it's a finite area somewhat bigger than this, like this, and it has some radius, which is denoted by R naught. So this R naught can be calculated from this formula, which is given by 0.61 into the wavelength of light used into the focal length of the lens by A, which is the half of the aperture. Remember, A is not the radius of curvature, it's the diameter of the lens, or the half of the aperture of lens, which is this. Now we'll move to another phenomena, and one of the last topics in optics, which is known as polarization. So what is the light? A light is basically an electromagnetic wave. It actually vibrates in more than one plane, and this light is called unpolarized light. But when this light is passed through a polaroid, the light vibrates. The light which comes out of the polaroid vibrates only in one plane. The light that is obtained is called polarized light. So suppose this is the unpolarized light. After it is passed to polaroid, it becomes polarized, which is like this, and it vibrates only in one plane. So now in polarization, we have to remember only one thing, that when unpolarized light is passed to a polaroid, the intensity of the light becomes half. Whatever the angle may the polaroid make with the light, it doesn't matter. The intensity always becomes half. When the polarized light is passed through the polarized intensity, the intensity becomes the cos square theta times the original intensity. So here, the angle made by the polaroid depend changes the intensity of the uh, light obtained after polarization.
To summarize wave optics, we have covered Huygens principle, interference, and Young's double slit experiment. Remember, Young's double slit experiment is very important. Then we have covered diffraction, resolving power of optical instruments, and polarization of light. With this, we end wave optics and the theory part. Now we will move on to solving problems.